Okay, let's dive right into this explainer. I want you to imagine you're standing in a high-tech control room, right? Suddenly, an unplanned shutdown alarm triggers across all the screens. The exact moment that system shuts down, an invisible clock starts ticking. And honestly, if you haven't calculated this clock in advance, you're flying completely blind. Subsea engineers call this the no-touch time. It literally tells operators exactly how long they have before the fluid trapped inside the flow line cools down into dangerous hydrate-forming territory. Get this calculation wrong, and what should be a routine shutdown suddenly turns into a multi-week, multi-million-dollar nightmare just trying to clear a solid, ice-like plug from the pipeline.
So that brings up a really crucial question. When is our flow line actually in the most danger of forming these massive hydrate blockages? A lot of people, they assume the risk is highest during normal, steady state production when fluids are just rushing through the system. But think about that for a second. When is the system actually the most vulnerable?
Well, the reality totally subverts our expectations. That steady flowing state, that's actually the safest state. While it's flowing, the warm reservoir fluid keeps the line temperature way up, safely above the hydrate formation curve. But the moment flow stops during an unplanned shutdown, that fluid is trapped. It immediately starts losing heat, cooling down toward the freezing ambient temperatures of the deep ocean. Because it doesn't have that constant influx of hot reservoir fluid anymore, the operating temperature drops straight into hydrate-forming conditions. And this brings us right to the absolute most urgent metric operators have: no-touch time. It is the literal deadline. It's the strictly calculated time window following a shutdown before that shut-in fluid reaches the critical hydrate formation temperature. And it's called no-touch for a reason. During this specific window, operators can try to correct topside facility problems or diagnose whatever caused the shutdown, all without having to take any extreme chemical or mechanical actions to protect the subsea system. Basically, it's their grace period.
The physics at play here are actually super intuitive. Just think about a thermos of hot coffee left on a cold kitchen counter. It doesn't freeze instantly, right? But it definitely doesn't stay hot forever either. It loses heat steadily until it matches room temperature. And how long that takes? Well, that depends entirely on how good the thermos's insulation is. Subsea engineers use the exact same logic, just with a fancy name: a lumped capacitance thermal model. It basically treats the trapped fluid as a single, uniform temperature block that's constantly leaking heat through the pipe wall and the insulation right out into the surrounding seawater, which is essentially acting like a giant freezing heat sink. So, no-touch time is definitely not a guess. It is a precise mathematical race against time. If we look at the lumped capacitance cooldown model, it calculates this window based on the fluid's mass, the thermal resistance, so the insulation, and the ambient seawater temperature. Operators rely on this exact formula to plan their shutdown response procedures for literally any hydrate risk flow line. It dictates the entire operational game plan. If they can fix the problem and restart within this calculated window, great, they're safe. But if they can't, they absolutely must intervene before that clock hits zero. Now, that mathematical reality brings us to a huge, absolutely critical warning. One of the worst mistakes you can make is treating no-touch time as just some fixed number that stays the same for a field's entire life. No way. It changes with the ambient seawater temperature, which we know fluctuates. It changes with the fluid composition, especially since the water cut increases as the well ages. And, most importantly, it changes with the insulation condition. Using a generic or outdated no-touch time is a massive planning failure because insulation degrades over time. It has to be recalculated and re-verified as the field ages. It's just not optional. To put this into some real-world perspective, let's look at operations in places like West Africa. Studies of platform operating experiences there show that a lot of typical process and instrumentation hiccups can usually be diagnosed and fixed within a specific 6 to 8 hour window. Because of that, subsea systems are often designed with just enough thermal insulation to guarantee the 6 to 8 hours of no-touch time. It gives the crew just enough of a buffer to, say, clear a sensor fault or reset a topside system before they have to take extreme remedial action. But as that clock ticks down, operators are staring at an intense decision tree. Step 1 is obviously the dream scenario: achieve a warm restart before the no-touch time window closes. But if they can't, they have to move to Step 2. They immediately pivot to injecting thermodynamic inhibitors, like methanol, straight into the jumpers and trees. And they start depressurizing, or blowing down the flow line. The whole point of blowing it down is to drop the pressure so much that the hydrate dissociation temperature falls below the ambient sea temperature. And finally, Step 3. If the shutdown stretches on and on, they have to completely displace the line with dead oil.
It is a highly complex, coordinated sequence, and every single move is dictated by that invisible clock. Okay, before we move forward, I want you to think about this for a second. Imagine we have two identical pipelines shutting down at the exact same time. They're carrying the same fluid, they're sitting in the same ocean at the exact same depth. Which one is going to give operators the most time on the clock before hydrates start forming? The answer ties perfectly back to capital expenditure decisions. A flow line with minimal insulation is going to suffer rapid heat loss, leaving operators scrambling with maybe just a few frantic hours of no touch time. But a line with high-performance pipe-in-pipe insulation, that dramatically slows the heat loss to the seawater. It buys the operators a massive 24 to 48-hour safety margin to troubleshoot without panicking. This is exactly why those upfront insulation investments completely dictate how much operational flexibility a field is going to have during an unplanned shutdown, even years down the line.
But what happens if the clock does run out and a hydrate plug actually forms? Well, hydrate dissociation is highly endothermic. That just means it takes a massive amount of energy and heat to melt the plug, which makes depressurization a really slow process. That can take days, sometimes weeks. However, emerging technologies are a total game changer here. Electrically heated flow lines can actively provide that heat, melting the plug right from the outside in. This active heating can clear a blockage in a matter of hours, letting you completely bypass the drawn-out, revenue-draining process of depressurization and blowdown. And that perfectly wraps up this module of our explainer. Every single threat we've looked at so far, from the physical wear and tear of sand erosion to the chemical breakdown of corrosion, the solid blockages of hydrates and wax, right down to the freezing cool-down clock we just talked about, they all converge into one ultimate goal: subsea flow assurance. It's all about getting the fluid from the mudline to the host facility safely and reliably for the entire life of the field. So I'll leave you with this final thought as we look ahead to the next section. We've spent all this time figuring out how flow assurance protects the fluids moving through the system. But what about the physical structures themselves? How in the world do we build and place the colossal manifolds, jumpers, and trees that have to survive the crushing depths, extreme pressures, and harsh environments of the ocean floor? Well, that is exactly what we are going to unpack next time.